Thank you. Thanks a lot. Today we will start a new subject. So I will mostly work on the tablet. I hope it's everything fine. I have also a couple of slides which I will use probably either at the end or tomorrow. So here is the subject of today, axion as dark matter. Okay, so first of all, let me introduce what is the axion. And the axion is actually related to the strong CP problem in QCD. So let me write. So CP problem in QCD. So let me review very shortly what this is about. The point is that in the QCD Lagrangian, you can add this theta term, as is called, I call it L theta, which is equal to the QCD coupling squared. So let's write it G3 just to take it, make it clear, is the QCD coupling divided by 32 pi square F mu nu, or G. Let me use G for the, I will use F as later on for the photon. So let me use now G for the gluon. So I have here G mu nu A, G tilde A mu nu, where G tilde is nothing else as the G multiplied by the completely antisymmetric tensor. So it's epsilon mu nu rho sigma G A rho sigma. Okay. So this term, you can see immediately, it's a term which violates both the T symmetry and the CP symmetry. So the easiest to see is the fact that violates, so this violates T and CP. And the fact that violates T is probably most clearly seen because you have this epsilon tensor where you have only one index, with one temporal index with 0. So this temporal index will tell you immediately that when you change the sign of time, you will also change, in instance, one of the derivative or one of the component of G will actually change sign. So the whole term here will change sign if you invert T to minus T. Similarly, you can argue about the CP properties, and you can also find out that violates also CP, so that at the end, of course, CPT is in total conserved for this term, but the single symmetries T or CP are violated. And if you want, you can see that it violates CP also because this term, if you would have F mu nu with electromagnetic field, this would correspond actually to a coupling of the electric field with the magnetic field. And you know that the electric field and magnetic field have different properties under a parity transformation. So you would have indeed that it also breaks the parity and therefore CP. Okay, so I hope this is pretty clear to everybody. Now, this term is also gauge invariant. You have here the trace, so it's the sum over AA, so which tells you this is it's a gauge invariant term, so there is no reason why you cannot add it to the QCD Lagrangian. And the problem is that once you add it to the QCD Lagrangian, you automatically open the door to the breaking of CP in the QCD sector. And one of the observational consequences of having this term is actually the fact that you have also some CP violating coupling for the pion. And this has also consequences, for example, so we can write explicitly one important observable, which is the dipole of the neutron. So if you have that term, you have practically a Feynman diagram, if you want, with a neutron, which comes in. You have a pion going here. You have, of course, here the neutron. Here you, for example, can change into a proton, and here you have a neutron. Here you have a pion. And one of these coupling, if the one of these coupling is one connected to this CP violating coupling, you find that you generate an electric dipole moment. And of course, here you have an emission of a photon, either from this of course, leg or for the other leg. And from this diagram, you get a contribution to Dn, which is of this order. It's the charge, of course. You have the mass of the quark, because it's if you want. You can rewrite that term by, in some sense, rotate it into the quark mass, divided by the mass of the nucleon, and the theta term. And of course, other constant, which I'm not writing here. And this term is, in some sense, a relatively, so that this coefficient here in front give you something which is of the order of 10 to the minus 15 theta ECM. Let me see, it is, yeah, probably it's 10 to the 16, sorry, I have a mistake here. So this means that you generate an electric dipole moment for the neutron, and we can also measure it. And we have limits of Dn, which are of the order of 10 to the minus 26 ECM. And this means that we have from this measurement already a hint, or a strong requirement actually, that theta has to be less than something like 10 to the minus 10. Okay, and this is indeed what is called the CP violation problem of QCD. Because generically from the Lagrangian, which we wrote before, there is no reason why theta should be so small. You have here a generic parameter theta, which can be anything. And since actually later on we will see it is actually connected with an angle, we would assume that this one is something between 0 and 2 pi, and there is no reason why it has to be incredibly tiny. Now, this is a discussion.
May I
yes?
ask a question?
Yes.
So it's a very nice question. So what we mean is that if we didn't have this Lagrangian theta term, we wouldn't be able to write this Feynman diagram?
No, we would not have this vertex. So this vertex here, so we would have this diagram, but only with vertices we do not violate CP.
I see. So we will have
so
the same diagram.
We have another vertex. So here we have actually only one of these vertices. You see, we have only proportional to theta. So these vertices generate a theta. So you don't see it immediately from this Lagrangian. It's a bit a long discussion to go to this, to really compute it, because the problem is, of course, here I wrote a theta term only connecting to gluons. But this is not the best way to use, or if you want, the more convenient way to express the interaction in the low energy Lagrangian, where you don't have the gluons anymore in practice. You have only pions and hadrons. Okay, so you need practical to make a connection to the chiral Lagrangian, and this you do because you can do a chiral transformation on the quark fields, and in some sense cancel this term completely, and move this theta term to the mass of the fields, in particular the quark masses. Okay. And this means that is actually why I have here this MQ, because this MQ term will gain exponential, or for I theta, if you want, which is actually giving me this term. And this will is exactly the piece which, if you look at the chiral Lagrange, gives you this CP violating vertex for the pion. If you don't have the theta term, of course, you have other interactions for the pions, but they do not violate the CP.
I see. Okay, thank you.
Okay. And as I said, it's a bit a long story. If you want to really see how this is computed, I don't have the notes to really do it here, but I can give you a reference if you want later on.
Okay, yes, it would be nice.
Okay, so this is one of the problems of QCD that, as I said, if you do not have this term, then QCD would completely conserve CP. But if you, as soon as you switch on even a small theta, you immediately get in trouble with the experimental measurement on the electric dipole moment of the Newton. Now, this is not the whole story, because of course we have CP violation in the standard model, and the CP violation is also connected to the quark masses, so that in fact, we also have another contribution, or if you want, even if we had here theta equal to 0, it's not completely true that we would not have a electric dipole moment and that we would not see any CP violation in QCD, because we have in principle a phase in the electroweak sector, and therefore also a complex phase in the matrix, in the mass matrices of the quarks. So this is practically the next discussion. So in reality, we have also CP violation connected to the quark masses. And in practice, this means that, as I said, you can see that theta and the mass instances of a quark are related in the fact that you can you generate, if you want, these so this initial term, and connected to a chiral transformation of the quarks. So in particular, you see that, so you can have a chiral U1 for the quarks, which is also called as U1A. So this means that you have, of course, the left-handed quarks and the right-handed quarks would change in the opposite way. So you have a usual transformation which would have a gamma 5 if you want. So you have a alpha of X in principle. Well, it will be a global symmetry. So let me use a global parameter here. And you would have here a gamma 5 psi, okay? Through a transformation of this type, you can see that you can generate the term which I showed you before, and you can also move around this theta term. So in some sense, I can move it from the gluon sector to the quark sector by doing a transformation here, for example, exactly which cancel the theta or moves the theta, part of the theta in this place. And it should be clear that since this is a chiral transformation, the mass term, so if you have a mass term which is a psi bar psi term, which is connecting left and right different chiralities of the fermion, then it's clear if you do this transformation, this is no more gauge invariant. Sorry, it's not invariant, it's not a gauge symmetry. So it's not invariant under this U1, because here, as I said, the left-handed and the right-handed component actually change in the same way. So here you get actually something like m e to the 2i alpha, if you want, psi bar psi. Okay, here I am using gamma 5 inside here so that to compensate the thing, plus Hermitian conjugate. And this means again that you have indeed the connection. So here, of course, I'm assuming here I have the quarks. Yeah, I have a connection between this term and the mass of the quarks. And indeed, in principle, one way I could also solve the problem of the CP violation in the strong sector would be to have massless quarks, or even if only one of the quarks would be massless, then I could do such a transformation on that quark, and I would in some sense be able to cancel out this theta term in the QCD Lagrange. Unfortunately, we know that from lattice computation that the masses of the quarks cannot be zero, or at least even the lightest one is not zero. So this solution for this problem is actually not viable. And we have, in that sense, this problem that we cannot just take one of the quarks to be massless. But due to the fact that you have this relation and the fact that you can move around, if you want, this theta term from the mass term to the gluon part, it's also clear that the real physical quantity is not either the theta term or the phase of the quark mass, but it's a combination of the two. So if you want, this is giving me the physical or physically relevant parameter is a combination of the strong, if you want, and the weak phase. And this is usually called theta bar often. And the theta bar is nothing else as theta plus the part, if you want, of phase, which comes from the mass matrix of the quark. So it's the argument of the determinant of the mass matrix for the quarks. Here you can immediately see the determinant of the mass matrix would exactly vanish in the case where one of the quark is massless. So in that sense, these would become again non-physical anymore, and then you could use it to cancel the rest. But as long as you have all the quarks which are non-zero, and in principle also they could have some phase in the eigenvalues, here you could get a contribution. And at the end, this is the relevant contribution which will actually give you also the electric dipole moment of the neutron. Okay, so in that sense, this quantity has to be small. Okay. Now, this term on QCD is actually connected to the vacuum structure of QCD. So this is also one thing you can explore in the exercises probably tomorrow. The fact that, yeah, so this term here has also a topological meaning. And in practice, you can check that if you add this to the Lagrangian, this is actually connected to field configuration, inequivalent gauge field configurations at infinity. So this is indeed this field configuration. You don't see it in some sense in a perturbative sense, because they are field configuration at infinity, which you usually don't access. So usually we expand everything around the field which vanishes at infinity. But yes, tomorrow you can see in the exercises, actually, even if the field vanishes at infinity, nevertheless, you still have inequivalent field configurations, because you have, in some sense, pure gauge fields, which will be different at infinity. And this term will give you a contribution which is non-vanishing for those type of fields. And yeah, and those configurations have practically different topological numbers, so that it's really a connection to the fact that QCD has a non-trivial vacuum structure. Okay, and this is true for all gauge group of the SUN type for n larger and equal to 2. So in that sense, if you would have the similar term, which we also explore for the electromagnetism, there in some sense is not the same story, because for electromagnetism, the term is actually trivial, and it is a total derivative which has no physical effect. So in that sense, there is no theta problem for electromagnetism, but there is a theta problem for a non-abelian gauge symmetry. Okay, so this is what I wanted to say a little bit about the theory. As I said, tomorrow probably in the exercises you can see a little bit more about these topological aspects.
I have one question.
Yes.
Could you repeat the explanation of that theta term for the U1 and the SU2 case?
Well, I mean, yeah, these would go into a bit more detail about the topology. So the main point is that you have to have non-trivial topological configuration of the field at infinity. Okay. And if you look at infinity in the case of the space that we have, which is a three-dimensional space, you have in some sense the three-dimensional sphere at infinity. And you need to map them non-trivially into the field configurations. So you need a gauge group which is sufficiently complicated to have configuration which have, for example, a similar structure as the structure of space-time, or space actually. This is the main component. So for example, gauge groups which have a subgroup which is SU2, as you probably all know, SU2 has the same algebra of SO3. So the structure at infinity in some sense, and the structure of SU2 and the structure of the sphere at infinity can be mapped in one another in a non-trivial way. In some sense, you are wrapping up the SU2 degrees of freedom into the SO3 sphere at infinity in a non-trivial way. Okay?
Okay.
And this, of course, you cannot do for a U1 because U1, topologically U1 is a circle. So it's not, it doesn't have the same topology as a sphere. So if you want, you can map a circle on a sphere, but the circle you can then always shrink to 0. So in that sense, for the case of the U1, this has not, you don't have a separate topological, if you want, in equivalent configuration, because all configuration at the end are trivial.
Okay.
Okay. We can discuss it further this afternoon if you want during the discussion, and I can also try to draw some pictures.
Okay, because this point is not easy to understand.
No, it's not easy, and unfortunately, I don't have the time to explain that. So that's why I put it in the exercises, because I think it's an important thing. But it's yeah, I mean, it would take me too much time. I want to cover the cosmology of it. Of course, this part is important, but it's not incredibly. Well, I mean, of course, it's in some sense you need this problem and this type of topological structure in order to have an axiom at the end. But what I want to concentrate on is not the theta term in itself, but the axiom.
Okay.
Okay, sorry for that. But as I said, you are welcome to ask me more about this in the discussion at 5 o'clock.
Okay, thanks.
Okay. Good. So the problem we have now is that this theta term, as I said, it's in principle any number, and we have to have it less than 10 to the minus 10. And as usually happens for theorists, the easiest solution to this is just to say, okay, well, why don't we set the theta bar to 0? And the thing is, of course, you could say, okay, let's assume this is just a parameter of the theory. We could put it to 0 and that's it. But this is not so incredibly satisfactory from the theoretical point of view. A much better way to deal with it is to make it a dynamical quantity. And this dynamical quantity then, in some sense, relaxes to 0 due to its property and its potential in particular in this case. And this is exactly the solution of this problem that was proposed by Peche-Quinn in the 70s. So that is the famous Peche-Quinn solution to the strong CP problem. This is make this theta dynamical. So how can you do that? Well, the simplest thing is, in some sense, to have another symmetry which is anomalous. So not only the axial symmetry connected to the quarks, but also, so you can add a U1, an anomalous global U1. And this is usually called Peccei-Quinn symmetry. Now, these global anomalous U1, we will discuss later. There are different realizations of it. And in principle, then you have different fields having charge under this anomalous U1. But in practice, the important thing is you want to break it spontaneously. So when you break this U1, as you probably all know, you always have still the freedom to move, if you want, in the angular direction. This is similar to a spontaneous symmetry breaking also, if you want, of a U1. Yeah, you can think about it also similarly to what happens in the standard model, even if here is, of course, a global symmetry. So what survives is actually a Goldstone boson, which is exactly the axion field. And I call it here phi, which is massless, of course, at this level, as long as you have not broken this symmetry in any other way. Yeah, so massless. And this Goldstone boson, since the symmetry is anomalous, will also couple to the same term, GG dual. So you would have, in some sense, apart from the theta, the Lagrangian, you also have this additional term, which comes from the fact that this U1 is anomalous. And if you break the symmetry, this anomalous term will give you something like some coefficient, the axion field divided by some scale, which is the scale of the breaking of the symmetry, times again the same thing, G square 32 pi square GG dual. Okay, so this is exactly the important thing, so that due to this additional U1 symmetry broken spontaneously, we also have an additional coupling. In this case, phi is a dynamical field, it's not a constant. So at the end, putting all things together, we have the following Lagrangian. If you want the theta, we have the theta term plus this anomaly term. So we have in total the coupling. So we have a G square over 32 pi square. By the way, I choose this value on purpose because this is actually the contribution to the anomaly for one chiral fermion. So this is why, in some sense, I have this quantity here in front. And then I have practically the theta bar plus this psi, this axion field divided by some scale. Where Fa is is called also often Peccei-Quinn scale, or is the scale where the U1 is broken. Sorry, I think I called it U1 Peccei-Quinn and not U1A, of course. The U1A is also used for QCD, so it's a bit a different story. Okay, so now it's clear what happens. This field is dynamical, so you can hope that it takes a vacuum expectation value in order to cancel exactly the theta bar. So then to cancel theta bar need to have the expectation value of the field phi has to be exactly minus theta bar Fa over Xi. Okay, and in some sense, in this case, this theta bar has no no physical meaning, in the sense that it's degenerate with this expectation value of the phi field. So in principle, you can redefine all this together to be this phi field, and just consider the behavior of a phi field connected to the GG dual term. Okay, so this one is actually what I will do in a minute. So, but of course, you could ask me, well, how can you do that this vacuum expectation value is exactly equal to this? Actually, you do not need to do much, because you have also the breaking of the U1 axial from the QCD sector. So as I told you before, you have practically this symmetry, the chiral symmetry for the quarks, which is a good symmetry as long as the quarks are massless. But when the QCD symmetry starts to be broken, you get actually a breaking of this chiral symmetry connected, even apart from the breaking, if you want, that you would have from the Higgs field, but you have a breaking just coming from the QCD sector. And this is in some sense connected to this U1A symmetry in the quark sector. And this would automatically give you a potential for the combination here, theta bar plus phi. Okay, and if you want this, you can connect it to instanton configuration. So this non-trivial topological configuration of GG dual, which in the case where you have this chiral breaking, they generate a potential. And at the end, the potential is periodic. So you have in practice this form of the potential, which is an approximation, of course, but it's this is what is usually used. So these are instantons effects. They generate a non-trivial vacuum configuration, if you want, GG dual term here, the vacuum expectation is not zero, and give a non-trivial potential for the axiom. And this gives if you want, the axiom potential, which is usually written as it's connected again to the chiral phase transition of QCD, so the QCD phase transition. And it is actually written usually as a cosine. And in the cosine, you have a combination of the two fields, as I said before. So you can write it as a theta bar plus psi phi over Fa. Or if you want, as I said, later on, I will assume that all these is nothing else as my axion field. So which, let me call it again, phi over Fa. It's clear that also the Xi coefficient I can reabsorb into the Fa, so it's not really very important. The only important thing to note is that in some cases here, especially for the you can have also the number of fields here appearing as because of the number of fields which contribute to the anomaly. And in that case, it can have a difference for the structure of the vacuum, and to that we will come back in a while. Okay, so this is in some sense is it's the axion, and this is the axion solution to the strong CP problem. Now you see immediately that this axion has a mass connected to the lambda QCD, because if you expand here, you see that the mass of the axion is practically coming from the quadratic term of the cosine. So it is, if you want, it is going like lambda QCD squared divided by FA. Okay, and this means, of course, depending on what FA is, these can be smaller or larger. Lambda QCD is of the order of 200 MeV or so. So if you put in numbers, you find here something of the order of 6 micro electron volt for 10 to the 12 in FA. And you will see in a minute why I concentrate on this quantity. Let me move this a bit to the right. So this one will be F divided by FA. Okay. Now, later on, we will also write this potential in a slightly different form, but this is exactly how it is generated. And here I just one mention of course, of historical perhaps importance. Originally, the paper of Peche Quinn did not really realize that they also had a physical field. They were practically only looking at the behavior of the vacuum expectation value, and they were mostly arguing the fact you can cancel the theta bar, but in some sense they did not really realize that they had an additional degrees of freedom. One has to say that in the 70s, the Goldstone theorem and all these things were not really completely known to everybody, and they were not standard law as today. But immediately after their paper, actually, they were Wilczek and collaborators realized that this is actually, there is also a degrees of freedom. So there is in that sense a field, and they called it actually, was Wilczek, chose the name of Axion. And the name Axion actually comes from a detergent in the US because they thought, okay, the Axion is actually wiping out or taking away this problem, and that is why it got practically used as the name of this field. Okay, and as you see here, this field is in principle a field which couples to the for sure to the QCD if you want to solve the strong QCD problem. But in principle, it could couple also to other sectors of the standard model. In particular, it can couple also to the SU2 gauge bosons, and it can couple also to the photon, so the FF dual P term. And exactly how it couples, it depends a bit on the model, on the realization of the model. So let me spend a couple of words about the models. So in that sense here, I just told you, I just get a, if you want a Goldstone boson and I couple to this term, but how could you generate it? So let me, yeah, so first of all, sorry, let me continue a little bit the history, the part. Historically, therefore, Wilczek realized that you have this field, and in the original paper, they were actually looking at FA values of the order of the electroweak scale. And this means, of course, if you put here something like the electroweak scale, then this mass is actually not so small, but also the couplings of the fields to the QCD sector is not so suppressed. In particular, this being a pseudo Goldstone boson, pseudo because here it gets also a mass. It turns out that if you really look at the QCD effective theory, so the below the QCD phase transition, you find out that you don't have only the axion, but you also have the pion, the pi zero, as a pseudo Goldstone boson, and with the same quantum numbers. So at the end, you have actually a mixing between the axion and the pion, the pi zero, so the neutral pion. And these, of course, will tell you that in principle, you would produce this axion field in any process where you produce a pion. This, of course, was not observed. So people realized relatively soon that there is no possibility that the axion was already, in some sense, produced or that it would be produced. So that at the end, this model that was proposed at that time was immediately practically ruled out. So that was the axion in some sense at the electroweak scale. But then immediately after, it was realized that the only thing you have to do is in some sense to push the scale FA higher. Because if you push the scale FA higher, then everything is suppressed by that scale. And so also the mixing with the pion, even if it's there, it becomes very small. So that in some sense was what saved the axion. And later on also, we realized that you need actually the scale to be large in order to have a substantial production of axions. So that's why here I'm also choosing this 10 to the 12 GeV. So the idea nowadays is that this scale is some kind of intermediate scale. And now then, let me come now to the models that were developed at that time. So models of invisible axion. I call it invisible because, of course, the fact that FA was large meant that it was not yet seen. And that's why they are called in this way. One model, it's very simple, and this is the one I will describe a little bit shortly here. This is what is called the ksvz model. And the ksvz is from the initials of the original proposals, which were Kim. Here was a single paper by Ginny Kim, and then there was a paper by Schiffman, Weinstein, and Zakharov. And this model is very simple in the sense that you just need to add one heavy quark, and in vectorial. In the sense that you add, of course, a Q left and a Q right. And what you do now is, of course, you can add to the Lagrangian something like a scalar field as usual, which I call here S. And then you have, if you want, Q bar Q. Okay. And this quark field, you give it different, again, you assume that it has a charge under the Peche-Queen symmetry, so that the left-handed component and the right-handed component, of course, have a different, again, this, due to this gamma 5, have opposite sign in the transformation. Okay, and in that way, you see that this term, in some sense, would again break the Peche-Queen symmetry. So the field S also has to be charged under Peche-Queen. So the simplest thing is to take, okay, here you have, you have this component, this combination, which is invariant. Here, of course, you can write also a coupling, so a kind of Yukawa coupling. And then what happens is relatively clear. The degrees of freedom of the axion is actually contained in this scalar field. So S is the scalar which breaks the Peche-Queen symmetry. So S is a scalar breaking the Peche-Queen symmetry. So what you have here is that the vacuum expectation of S becomes equal to FA, and the degrees of freedom, if you want, contained in S, of course, you have a radial degrees of freedom, but it's usually very massive. So people, if you want, you can also forget about it because it gets also a mass of order FA. What is important is that you have the angular degrees of freedom. And of course, the angular degrees of freedom is exactly the axiom. So if you want, you can write, let me write it in the next slide. You have S, you can write it as F phi over, if you want, square root of 2. Here you could write it as with a radial part. And then you have the angular part. So here is exactly the axion field divided by FA. And through these, you can see exactly what are the couplings of the phi field. And you can realize that, as usual, as a Goldstone boson, it will have derivative couplings in principle to all fields which are charged under the Peche-Queen symmetry. But now you can ask me, how do I generate the GG dual coupling? Well, the GG dual coupling you actually generate from a diagram, from the triangle diagram. So this is exactly the usual discussion, if you want, of the anomaly. Here you have a triangle diagram with the heavy quarks. And here, of course, you have the gluon, because this is a quark. So it's a non-trivial representation of QCD. And this diagram at low energy, the only thing in some sense which connects here, it's nothing else as the axion. And this term here, if you compute it explicitly, you can compute the loop. This gives you exactly, if you want this loop, is exactly the same computation that you can do for the ABJ, so the Adler-Bell anomaly. So that is exactly the same computation. And you get out of it nothing else as exactly phi over FA, the famous 32 pi squared coefficient, and the G squared, and you get this G tilde. Okay. And you see therefore that here it's pretty simple. You just need one additional heavy, you have a heavy vectorial quark, so with left and right-handed component in the same representation of QCD, but with different, or if you want, with an axial transformation, so that for the Peche-Queen symmetry, the charges in some sense are not the same. And this is in some sense is one of the simplest the models you can think of. And from this diagram, you can immediately see that you could also draw the other diagram, which we will find also later, which is the connection, of course, to the photon. Here, if you have quarks, generically quarks can have also electromagnetic charge. They do not have to, but of course, you could also choose here Q, the heavy quark, to have no electromagnetic charge. Then in principle, this diagram would not be there. On the other hand, you always have, as I already told you, a little bit of mixing with the pion. So at the end, a little bit of coupling with the photon you will always generate. So this coupling here would give us a similar thing, but for the electromagnetism. 32 pi square phi over FA FF dual. Okay, and I spent some time on this because, of course, these coupling are the coupling, or especially the second one, is the coupling that you hope to exploit in order to see the axiom. Because, of course, it's in that sense, it's much easier to devise experiments based on electromagnetism. And indeed, later on, we will see what type of experiments are being done to measure the axiom connected to the coupling to the electromagnetism. But generically, as I said, if you want, let me finish with the very short thing about the Axion coupling. So in some sense, the Axion coupling are of two types. So you have, if you want, these anomalous coupling, so the GG dual, the FF dual. To gauge bosons. And this is also, I mean, in some sense, it's typical of a pseudo-Goldstone boson. So it's generically true also for Alps, if you want, or for things of that type. And then they have, in principle, derivative couplings to all field charged under the Peche-Queen symmetry. And in principle, these derivative couplings, you can turn into couplings to the mass term if you want. So these are also in some cases, if of course, if you have a derivative on the axion, you can do a partial integration and move the derivative towards the other fields. And then deriving those fields will often give you actually the mass term. So So in some cases, this is equivalent, but not always. So yeah, so if you want connected also to mass. To the mass coupling, if you want. Okay, and this in some sense is what makes everything very predictive, because due to the symmetry in some sense of the field, these are only the type of coupling that you can have. Plus, of course, due to this anomalous coupling, the potential I gave you before. So the potential will, of course, play a key role in the description later on. Now, for completeness, let me just mention another model, which is called the DFSZ model. And in this case, the authors were Dine, Fischler, Zrednicki, and Zitnicki. And in that case, the idea was different. Instead of having the heavy quarks, you give a Peche-Quinn charge to the standard model fields. And here also there are different realizations. You could just, for example, one possibility would be to give Peche-Quinn charge only to the right-handed quarks. Or again, you can give opposite charges to right-handed, left-handed quarks or whatever. Of course, you need to give a charge to the quarks in order to have, again, the anomalous diagram I showed you before, to give the GG dual type of coupling. But of course, you could have also coupling to the Higgs and coupling. Of course, if you give a Peche-Quinn charge to the quarks, you have to give a Peche-Quinn charge also to the Higgs. And of course, you could also have the leptons having a Peche-Quinn charge, again, connected to the fact that the Higgs has a charge. So in that sense, for this type of models, you need to have, for example, to extend the standard model to have two Higgs doublets, because you need, again, a different Peche-Quinn charges for up quarks and down quarks. So it's in some sense, it goes a little bit in the direction of supersymmetric model, which also have two Higgs doublets. But the important thing is, of course, that you have the same diagram as before. So in this case, in the loop, you have standard model fields. So you have, for example, just the quarks. And then, of course, in principle, you have, if all the quarks have the Peche-Quinn charge, then here, of course, in this result, you have also a factor of n number of quarks. Now, this factor of n, you would think it's not so important, but actually it is, because it changes also the vacuum structure. So in the case of the presence of this n, if you have many fields which run here in this loop, what you find out is that the also in some sense the periodicity changes, and you have a periodicity period which is shorter by 1 over n. And this means that if you look at the usual range of from 0 to 2 pi, you have a kind of Zn symmetry, and you have a n vacua instead of having only one, if you want a vacuum with the 0 value. So this, in this case, so then if you want the U1 Peche-Quinn gets broken not into nothing, but it gets broken into a Zn with n-degenerate vacua. And this is important also. Later on, we will come back to this for the cosmology, of course, because this will mean that you can, for example, produce domain walls between different vacua if you have the Peche-Quinn phase transition late enough in the cosmology. Okay, I see that I am nearly at the end, but yeah, so maybe I can do the break here, and then I will start to discuss the cosmology and in particular how to produce the axion to be the dark matter. So are there any questions on this part?
I have one question. I mean, at first, after after the breaking of Pidgeot-Quinn symmetry, the axion is a massless
Yes.
Goldstone boson. So the I mean, after the condensation of the quarks, then the axion got mass, right?
Yes, yes. This is exactly what I will discuss in the next part. And this is the important point. Yes.
Okay.
So more questions?
I have a question, sorry. So we wrote that in principle, the axion can couple to the photon through FF dual.
Yes.
But I thought that FF dual could be reduced to a boundary term for the QED, and that would be...
Well, if you have a constant in front, but here you don't have a constant, you have a field.
Ah, right, okay, yeah.
So the constant part, so the theta part does not have any if you want, a physical effect on anything in electromagnetism. But of course, if you couple to a field, then it's another story.
Ah, okay, okay, thank you.
Can I ask a question about
Yes,
the ksvz model?
Yes, I can go back.
Yes, thanks. Essentially, we are saying that S is the scalar field that breaks Pidgeot-Quinn symmetry. So essentially, there is a potential essentially in this model given for the S field.
Well, yes, I mean, in the original models, the people were not really discussing a lot about the potential. In principle, you could think that there is the usual potential like for the Higgs. Okay. But of course, you could also have a description assuming, as I said, usually the scalar part, so the radial part, you are not really very much interested on. So in some cases, you could also look at the description connected just to the, if you want to do a similar description like you do for chiral symmetry breaking. So in that sense, using only the light degrees of freedom, which is phi.
Okay, okay, okay.
You have in mind what I mean? So in some sense, you could, in some sense, assume that there is no radial degrees of freedom, and you send the mass of this field to infinity and integrate it out if you want, and then look at what remains.
Yes, yes, of course.
Yeah. So that's why, I mean, I didn't write a potential because usually the potential is not so incredibly interesting because it just related to the radial degrees of freedom. And the radial degrees of freedom is usually assumed that it's very heavy. So, and in some sense it's taken away yeah, so it's neglected.
Thanks.
Okay, so yeah, so in some sense, yeah, you could go directly to the nonlinear realization of the symmetry if you want. So that's what I meant before.
Can I ask a quick question?
Yes, of course.
So apart from the couplings to the bosons, you said that we also have derivative couplings to the rest of matter fields. Do we expect these couplings to be suppressed or less relevant than the couplings to the bosons, or do they also have some phenomenological consequences?
No, they have phenomenological consequences. And of course, the scale of suppression is the same, it's always FA. So because you see this field phi always enters like 1 over FA. And of course, as I see, it's again connected to this. You can always do a Pidgeot-Quinn transformation with the parameter equal to the phi over FA and move around, if you want, terms from the derivative piece to the GG dual, etc.
I see.
So there is, in some sense, a kind of, yeah, if you want, yeah, you have different ways of parameterizing sometimes the same coupling as well. But generically, as I said, if you have as a Pidgeot-Quinn charge field, you would expect it to have, in principle, a coupling to the axion. connected to the fact that you can, so this symmetry I was saying before, so where is it? I forgot. Yes, so you could take again here an axial symmetry here with the axion field though. So then of course it will not be a global symmetry transformation anymore because the axion is space-time dependent, but that means that this will show up also every time you have a derivative.
I see.
And this is exactly that from the kinetic term gives you the derivative coupling of the axion.
Ah, okay, okay.
And moreover, as I said, for example, in a mass term, you have explicitly also here, if you would have this transformation, you would have also a explicit dependent of the axion if you do a transformation on the fermions connected to, which is proportional to the axion field.
Okay, thank you.
Yeah, so I didn't want to go into the detail about this, but you can, in principle, see what are the relations among the coupling depending on what type of field you have and what charges they have. And just as a final comment, of course, in this ksvz model, since the quarks here, you see that you get an Fa here. So the quarks QQ bar gets a very heavy mass, again, of order Fa. So that's also why usually also these fields are integrated out. And at the end, you're left only with the axion. Okay, so in some sense, you forget about the presence of all this sector, and what is left with you don't have really other couplings apart for the GG dual or FF dual coupling. But for the other models, it's not like this. Okay, more questions? Okay, let me save the slides before I forget, because yesterday I actually forgot to save them. Yeah, let me go now to the cosmology. Okay, so and this is maybe the most interesting part, but now the first thing you could ask me, and indeed is the first thing I will discuss, is can I produce the axion as a thermal relic? So this is indeed what we discussed yesterday and the previous days for example, for the WIMPs. And the question is, can be the thermal relics? Well, the axion generically couples to everything with this 1/Fa coupling, but of course it can be produced. So this is exactly the point. Yes, so it can be produced by scatterings. So in particular, I can draw a couple of them. Of course, you have this vertex with the gluon. So for example, you can have a gluon coming, then you have this vertex. The gluon interacts with anything else. Here you can also have a gluon, not a quark. And then here you can have an axion produced. Or you can have the even simpler diagram of the annihilation of QQ bar into an axion and a gluon. And etc., etc., etc. So I don't draw all possible diagrams, but all these diagrams would actually produce the axion. And you see immediately also that in this case, I do not have a Z2 symmetry for the axion. So I produce a single axion. So in some sense, you would have to modify a little bit the equations I gave you earlier, by the fact that here you have a production of a single axion and not two axions, because you don't have any Z2 symmetry. Indeed, the axion is actually, we will get to that at the end, it's a decaying dark matter candidate, because it's clear that through the coupling, for example, to two photons, you have the decay of an axion into two photons, similarly as you have the decay of the pion into two photons. So in that sense, yeah, we'll see later on why we don't have to worry about that. But generically, the axion is not stable and it's not protected by any Z2 symmetry. This means that in this case, I have to solve a slightly different equation. which is this brings me to the mechanism. So this actually, Axiom was one of the first WIMPs. So WIMP is a feebly interacting massive particle, which is also in one of the exercises, and you can find there more details about it. So this means that you produce the particle from an interaction which is very suppressed. And if you want, you can write again the Boltzmann equation for the axion density. It is the same as we had yesterday or the day before. And in this case, though, we have these processes with one single axion. So here you have actually gamma. This gamma is nothing else as the rate of these processes which produce an axion. And this is then proportional to the number in equilibrium of the axion minus the number explicitly of the axion. You see immediately you have the same structure as we had before, and in principle you can derive it exactly in the same way we did it for the WIMP, only that you have to take into account that you have processes with a single final axion. And this N equilibrium is actually nothing else as connected to the fact that the initial state is exactly in equilibrium. So this type of distribution is connected to the initial distribution, which is thermal. And so the axion here is not supposed to be, or at least we don't know if it is in thermal equilibrium or not. Now the gamma again is in this case just the sum over all processes of the number, the equilibrium number density of the standard model particles times the cross section for the particular process. And in this case, this cross section is actually, the estimate is pretty simple. I'm not going to do the computation. I actually tried yesterday to do the proper computation, but it would take me too much time. But you can see immediately that sigma v, in this case, you can estimate it. Since you have a non-renormalizable coupling, you can see immediately that if you look at these diagrams here, you have this vertex, which is exactly this 1 over FA times the G squared over some factors of pi. But here you have again another gauge coupling. So at the end, what you obtain is something which goes like the strong coupling constant to the cube, divided some pi factors, and 1 over FA squared. And again, you have exactly the right dimension. And alpha S, of course, here is nothing else as the G squared divided 4 pi. And you see, therefore, that depending on this coupling, you can have here stronger or weaker behavior. And here you see this, you have a 1 over FA squared. So here is actually no dependence, if you want, on the velocity. If you take the average, it would not change because this is a constant. So it's similar to the WIMP case where you have the cross section as a constant. And this term here gives you actually a T cubed dependence if you are in equilibrium and a massless particle, which is a good approximation for quarks and gluons at high temperatures. So this one would also go exactly like this term. So if you want the sigma v times a T cubed, or xi, if you want, you can keep also the xi over pi squared T cube. And from this, we can do immediately the kind of back of the envelope computation. So we can check what is the, if you take gamma of order h, remember that h, we had it also is pi over 3, this square root of g star over 10 t squared over Planck's scale, the reduced Planck mass. So if you want, you can equate these two quantities. So this one goes like t to the cubed, this one goes like t squared. So you see immediately that you have equilibrium only if the temperature is sufficiently large. So you need actually t larger than 8 pi squared over alpha s cube FA square over the reduced Planck mass. and plus some numbers, some factors which I don't rewrite. And if you put in all the numbers, so you see here you have an FA square over M Planck. So this is, M Planck is large, it's 10 to the 18 GeV, but FA is usually also not so small. So if you plug in numbers, you can get something of this type, is 5, 10 to the 11 GeV, FA over 10 to the 12 squared. Okay, so if you have FA in the intermediate scale, you can obtain an equilibrium distribution of axion if you are sufficiently high in the temperature. The problem is if you are at such a high temperature, it's of course the mass, there is no mass of the axion in that sense. So when you produce them, you are massless. And later on, of course, at the QCD phase transition, you will get a mass term, but in order to have the correct omega h square, you will need a relatively small mass. So if you want, you can estimate here the number of axions in this. So y of axion is in this case just equilibrium distribution at that temperature. So it's pretty easy to estimate. You have a 45 divided 2 pi squared. This is connected to the entropy. Remember, y is the number density divided by entropy. And here you have the degrees of freedom of the axion, which in this case is just 1. And here the GS at the temperature TD. So this is a fixed number. And as I said, at the end, you can just compute very easily the omega h square. And they give you here the final result for the thermal distribution. You see that if in order to get something of order 1, you have to need a mass of the axion of the order of 0.2 electron volt. Assuming you have 100 degrees of freedom, which is usually, I mean, if you don't have anything else as a standard model, this is satisfied. Of course, if you would have additional degrees of freedom like supersymmetry, you could have a bit more degrees of freedom, but that's the more or less the ballpark number. So this means that you need a very small mass. Since you are decoupling very early as a relativistic particle, you get a huge number of particles. This means you need a small mass to have the right dark matter density. And this means that this is a hot dark matter. So need a very small mass to match the dark matter density, energy density. And this means nothing else, as here you have hot dark matter. So it is, or if you want, yeah, it's even lighter than a neutrino in some sense. Of course, we saw the other day the neutrinos have to be in the electron volt region. In this case, instead, due to the fact that you have more degrees of freedom, you have even smaller mass. So which means that you really have below the electron volt. And this means in this case, of course, this is not a good dark matter candidate because we know structure formation would not go as we need it. So not yeah, the correct structure formation history. Okay, so in that sense, this is actually excluded. Of course, you could do something else, which is exactly in some sense the WIMP. So you could assume that it's not in equilibrium, so produce this as matter through this equation while the particle is still out of equilibrium. So for temperature below this 10 to the 11 GeV. And this is indeed also this one thing you could try to compute from the exercise. It's of course a possibility. Then of course the mass could be larger because if you produce the particle not in equilibrium, the number density will be smaller, so you have to compensate with a larger mass. But nevertheless, it's a bit difficult to go very far. So in that sense, yeah, so here you have below the electron volt, actually you have to go below 0.1 even electron volts. And if you have the WIMP mechanism, you could push it to higher value, but you still have the problem that you are in trouble to, even if you go to the more warm dark matter than hot, is still probably difficult. Okay, so luckily we have a quite different mechanism to produce the axion, which is automatically giving us a very cold axion. And it is in some sense built in the evolution of the universe, and is not very much dependent on exactly how the axion couples and anything. And this is the misalignment mechanism. Now, the misalignment mechanism is based on the fact that the potential, as we heard before, the potential of the axion changes in some sense in the evolution. And originally, practically, you do not have any potential. So the basic idea is the following. You start, in particular, during inflation, where the axion has no potential. So in some sense, if you look at the axion field, the potential is 0. So the axion field can be any value. And as again, assuming that the axion is actually a periodic, so here I will look only to minus pi to plus pi. Well, let me draw it a little bit better. So of course, here in this parameter space, here what I am plotting is phi over Fa. So this domain is actually minus pi and pi in units of Fa. And here the potential is completely flat. So this means that you have a scalar field which could be anywhere in the universe, especially if you have an inflationary phase. We will see it in a minute. The field, even if it would be moving, if we start with some velocity at the end, we'd get stuck somewhere in this field space. So for example, you could be here. But then you, so this one is at high temperatures or during inflation, if you want. So you need, you probably also don't even have a temperature. So here in the inflationary epoch. So during inflation. But then after inflation and later on, what happens is you generate a potential. So if you generate a potential, you have, for example, that now the potential would look like something like that. Okay, then at the end here, it's of course a cosine. So it will look like this, minus pi and pi. And if you were here, you would start to go towards the minimum, and the minimum has to be a 0. This is exactly the solution of the strong CP problem. But then the field will start to continue oscillating here around the minimum. And when it oscillates around the minimum, this will behave exactly like a cold dark matter candidate. So, and this is practically, it's a condensate as cold dark matter. Okay. And this is exactly the misalignment mechanism. It's called misalignment in the sense that the vacuum state during inflation is not aligned with the vacuum state at the end, which is actually 0. So that in that sense, you have exactly also the same relaxation that we need to solve the strong CP problem, but not only, because the relaxation will be very, very long-lived. And this is exactly the thing we will get to discuss in a minute, how exactly long-lived it is, this oscillation. So how can we solve this behavior or this dynamic? So we can consider the field evolution in the Friedmann-Robertson-Walker metric. And of course, the equation, I don't derive it. I think this is also one part of the exercise in principle. The equation we obtain is nothing else as the Klein-Gordon equation, but with an additional piece. So we have the box operator on the phi field, plus we have the usual 3h phi dot field, which comes from the fact that we have non-trivial connection. And then we have the derivative of the potential. And this has to be equal to 0. So it's clear, therefore, that you have, in some sense, of course, the potential can be there or not, depending on what epoch you are. So, and we can look at the solution of this equation in two different epochs. In the early universe, in particular, assuming that you have inflation, this term, as I said, the potential is not present, but the Hubble parameter can be also very large. So this is exactly what we have during inflation, assuming the scale of inflation, of course, is larger than the scale of the QCD phase transition, which is usually the case. So we have V prime is equal to 0 and H is equal to constant. And it's the Hubble parameter during inflation, which is more or less constant. In that case, this equation especially for the, if you want the 0 mode, so the equation becomes the following. We have the second derivative of the field plus 3h, the first derivative, is equal to 0. And this is for the homogeneous part. And the solution of this equation should be well known to everybody. H here is a constant, so this is nothing else as a damped, if you want, oscillator, but not even an oscillator, because of course here you can solve for the first derivative and you get immediately that the first derivative is equal to the initial condition times e to the minus 3ht. Okay? So you see that you can start with a non-vanishing velocity in the field. The velocity will immediately or very quickly go to 0 due to this exponential suppression. So what happens is exactly what I was telling you, that the field phi will be practically constant. So it will be stuck in one particular point. Of course, we don't know which point it is, but it's just one initial condition in some sense, one particular point, which is constant. And this is exactly the picture I had here. So the field gets stuck at a particular initial condition, which I will call later on also theta I, so the initial value, if you want, of this angle. Now we have to look what happens later. So now consider the behavior after the phase transition in QCD. And in that case, of course, the Hubble parameter, so in that case, the QCD phase transition happens at temperature below 1 GeV or so. So the MEV is the scale of lambda QCD. So this means that we are relatively late in cosmology, and we are, of course, after inflation. And we have, in this case, the Hubble parameter is actually the Hubble parameter of radiation. So Hubble is given by radiation dominance. And the equation, of course, is the similar. So for the 0 mode, So the k equal to 0 momenta part of the field, we have again a similar equation. We have the second derivative, we have 3 times h, the first derivative. And then we have the potential, which in this case, of course, it's coming, I can write it as a mass squared as a function of t. I can write it like a fa and a sinus of the, of course, a of t over, phi divided by fa. And this is in principle the equation I have to solve. Now solving it for a sinus is not so easy. So usually what one does is to expand it to keep only the quadratic term. And we get, again, harmonic oscillator type of equation, only that here h is time dependent. And here we have also a time dependent mass, because during the phase transition, the mass will not be constant, will grow with a particular behavior with temperature, for example. And indeed, one can look a little bit at what this mass does. So, so we need the behavior of the mass. Of course, you could solve it with MA constant if you want. This is an approximation which is not so, I mean, it's not exactly the correct result, but it does make not a huge difference. So this m square of a of t, you can actually write it more easily as a function of the temperature. And this is practically 0 as long as the temperature is larger than the QCD phase transition, which is approximately above 1 GeV or so. And then below that, it starts to grow slowly, but it grows actually, well, it grows slowly up to a certain point, but it's, there is a dependence on the temperature, which is of this form. So you have a scale here, which is connected again to the lambda QCD scale. You have a 10 to the 12 GeV over FA. And then you have the temperature to the 1/4 power for temperature below the QCD and up to the saturation, of course, the saturation temperature, which is lower. Of course, at a certain point, it will become constant. If you are sufficiently below the phase transition, this will be exactly MA fixed by the lambda QCD if you want. So lambda 4 QCD divided by FA. Okay. And this happens for temperature. It's relatively quick. You see here the dependence is at t to the -4. It means that the mass grows pretty fast. There have been also a couple of years ago a few discussions that maybe the dependence is not exactly t to the 4. There were also people proposing slightly different behavior, but at the end it does not make a huge difference in the number density of the axion. So the real behavior is not so incredibly important. The important thing is, of course, that in order from the equation you have here, in order to have the oscillation, you need here to have a mass term which is substantial with respect to the Hubble parameter. Because as you see here, the Hubble parameter will actually try to slow down things, and it is the mass term which will give you the oscillating behavior. Now, from this equation, you can also see that we can actually play a little bit of trick and take out, if you want, this 3h phi dot dependence. Indeed, this is exactly what we can try to do. So we see that we had already the behavior before. So if you want, well, I can give you the result because I practically know what it is. So I can take the field and rescale it. So I can write the axion field as a function of time. as the scale factor to the 3/2. And then I use another field, let me call it chi of t, which is the rest. And then you see that if you derive this one, you get, you can derive this one and you get a 3/2 Hubble chi of t. Oh, sorry. Of course, you get 3/2 a dot, you can derive it by a, and then yes, and you have then let me get the expressions correct. So you have derive a 3/2, then you have a to the 1/2, but then you can write the derivative as a over a. So here you have again a, no, sorry. And then you have, of course, this a to the 3/2 chi dot. Then you can take the second derivative. And then again, if you take the second derivative, you get a second derivative of the scale factor, which gives you this part in practice square, assuming you have also the derivative of the scale factor itself. So 3/2 h dot. And then you have since you can derive also this one once this scale factor, you have actually 3h a 3/2 chi and dot. And then you have here the second derivative of the chi dot, chi double dot. And from this, you see that this expression here is exactly, in some sense, canceling out the 3h phi dot that you have in the previous expression, so that at the end, you get an equation which is, in some sense, a bit simpler. So you have at the end, oh, I am again at 20, sorry. I have to save. And then I have to go back to the beginning probably, or let me cancel perhaps this one because I probably don't need it very much. So here I can rewrite the equation I had before, and I get something like phi double dot plus some kind of omega square of t times phi is equal to 0. Where this omega square is a sum of all these additional terms. So you have, of course, the mass term, but you have also the Hubble term, which I wrote before, this one, 9/4 h square. And you have also the term with the h dot. Okay. So you see, sorry, here I should use chi and not phi anymore, of course.
Sorry,
So,
can I ask a question?
Yes.
In order to cancel the Hubble term, we have not to renormalize phi with the minus 3/2.
Let me think. Yes, sorry. Yes, you're correct. Yes, minus. Yeah. Of course, it's the volume at the end. That is important. Sorry. Yes, you're completely correct. So you have here a minus, and here you have a plus because it's squared, and here you will have a minus. Yeah, sorry. It's a very stupid mistake. And here you get also a minus. Yes, otherwise they would not cancel the term on top of it. And here you have a plus. Yes, sorry. Yeah, I must admit, I have it written slightly in a different way, so I have to move. Yeah, I wrote it in the other way around, so that's why I had the wrong exponent. Yes, you're completely correct. So, but this equation should be correct apart from this sign here. So you see that you get practically an harmonic oscillator with a periodic mass. Sorry, periodic with a time-dependent mass. So in that sense, you can write the solution in a relatively simple way as chi of t is something, assuming that this mass changes slower than the frequency of this oscillation, which is again given by the mass, you will have something like a constant over even if you want to be you can rescale it in this form, and then the cosine of the integral of the omega. Okay, so this one is nominally the solution, and as long as you can approximate this one to be not very strongly dependent, this will give you a real oscillation. So in reality, you have at the end, yeah, so if you want the solution for the field, you will have also the additional scale factors rescaling. And again, this cosine, which in the cases where this, first of all, is dominated by the mass, and especially when the mass then becomes constant, what you end up with is actually a real oscillation with the mass. So it will at the end become a periodic motion around the minimum. Okay, and this solution already tells you two things. First of all, you can use it to estimate the number density in this field, because of course we will have this field does not interact with anything, and it's practically just an oscillator. So we can get an estimate of the energy density by assuming that, of course, at the beginning you would have a Hubble expansion, which probably decreases the energy density. But on the other hand, later on, when you have the oscillation, the dominant contribution will be exactly this dilution by a to the minus 3/2. So if you want, let me, yeah, so what do I cancel? I cancel this one, I think. So I would have then that the density, of course, in the axion, the energy density would be nothing else as 1/2 ma square, the field square, plus the kinetic term, so plus 1/2 the, if you want, phi dot square, because here we don't have any term which is connected to the spatial derivatives. And if you solution, you will find that the cosine and the sine square will cancel out. So this one will give you nothing else that the constant here square, the mass squared, and the a to the minus 3. Okay, so this means that the energy density does scale as matter. So a to the minus 3 is exactly the matter scaling. And this means you can see that with that, cosmologically, this is equivalent to having a particle which is non-relativistic. In this case, of course, the particle is non-relativistic, but it's also not really a particle, it's a condensate, because you are looking at a field value which changes, and you can, of course, interpret it as a number of particles, but it's not really incredibly necessary. You can, for example, yeah, so if you want to interpret it as a number of particles, you can estimate the number of particles by dividing rho a by the mass. So this would be more or less the number of particles, since it is a non-relativistic, so you don't have any momentum. So this will tell you that this is actually a 1/2 ma a value at the time, of course, where you start the oscillation. which I call it time 1, times the value of the field, so the phi square at this time 1. And this is the value of the number density at the beginning of the oscillations. So yeah, let me just write T1 because otherwise it's too long. So in some sense, if you see here, you start really to oscillate when this term here dominates with respect to the others. So what you have to compare is always the comparison of the mass with the Hubble parameter. So, so at T1, where you have the mass of the order of Hubble. And therefore, if the mass is of the order of Hubble, then it's clear that here you could also use the Hubble parameter if you prefer. And the Hubble parameter is also connected to the time. So this you could also estimate more precisely. This phi square is nothing else as the initial condition, if you want. So phi square of T1 is nothing else as the value. So I will call it, if you want, theta I square, the FA square, which is exactly, if you want, the value of the field, which we had in the plot here. So this value here, which is nothing else as I said, theta I, the initial value of the angle. And therefore here you have an estimate for the value of the number density at the time T1. And you can easily see that this number density is conserved because there is no process at the moment, apart from the decay, which we discuss in a minute if I have time to do it, otherwise we discuss it tomorrow. But for the moment, assuming that the number density is conserved, then it's clear what happens for the energy density. So this is, so the number density or the number of particles is conserved. So if you want to keep that, this means, and let me erase another slide. I think this one I could erase. So we have at the end that we get the density of the from the misalignment mechanism for the axions is actually nothing else as this energy density, so the number density of the axions at the time T1 multiplied by the mass today. So if you want, let me do it in a different way. So this is the number density. I rescale the number density to today. So this, of course, rescaling this means to multiply by the scale factor. I have the scale factor of T1 divided by the scale factor of today. And I have to, of course, consider the cubed value. And then I have to multiply by the mass to get the energy density. And then since I want omega, I have to divide by the critical value of the density. So rho C and actually over H square. Okay, so this one is the expression I have to evaluate. As we have before, we can plug in NA, and I wrote it just in now. I had MA at the time T1, and I had in principle the initial theta I, the initial value square, and FA square. And then, of course, I have this rescaling by the scale factor. And then the mass divided by the critical density over H squared. And now this A of T1, it's again connected with the time where the mass is equal to the Hubble. So I can use the expression for that, which is, yeah, so in principle, I have an expression which gives me that the condition gives me this particular time. And this is connected with the, yeah, so I can give you the explicit value 10 to the minus 7 seconds times FA over 10 to the 12 GeV to the 1/3. And this is exactly a relation that you get from assuming MA is equal to H of T1. Remember, we are in radiation dominance, so H is actually 1 over 2 T1. So it's relatively simple in that sense. And if you plug in this here, and you also rescale here the scale factor out, which of course depends also on the time, is in radiation dominance, the scale factor goes like T to the 1/2. You can at the end rewrite everything as a function of FA, and this is probably my final result for today. You get something of the type 0.15, the theta I squared, but FA here is only to the power of 7/6 because of this cancellation between different contribution. Okay, so this one is the estimate, and you see you have a strong dependence on the initial angle theta I squared. You have also not so strong, but 7/6 dependence on FA. And you see that here you're exactly, that is the reason why I chose 10 to the 12 earlier, because you see that for values of 10 to the 12 FA, for theta of order 1, I get exactly in the right ballpark of the dark matter density. And that in some sense is also one success. I don't have to do anything, just looking at the motion of the axion in the early universe, I automatically get more or less the right number density. Of course, this is not the end of the story. Indeed, the next I will discuss tomorrow, because now we are already at the end of the lecture. There is one point I have to check, and this is the fact that the oscillation has to be long-lived enough to be still around. And this will not be a problem, but tomorrow we'll compute the decay rate of the axion if you want. And then the other point is that now I didn't discuss anything else about inflation and when we break the symmetry or not break the Peche-Quinn symmetry. And this will be another discussion we will have to do tomorrow, because of course this value of theta initial will depend on exactly when I do break the Peche-Quinn symmetry in the cosmological evolution, in particular before inflation or after inflation. And this will also have a couple of other consequences. In particular, if you have also other things happening, for example, formation on topological defects, like since we saw if we break a symmetry, it's a U1 symmetry, we could have strings appearing. And also we can have, in the case where n, in the DFSZK model where n is larger than 1, we could also have domain walls forming. And of course, this is, can be quite a problem for the cosmological evolution. Okay, so this one is what we will discuss more in detail tomorrow. And so I think today I will stop here. And of course, I can answer questions now, but we can also discuss them also later in the discussion.
So thanks, Laura. I want to read a question. We have a question on the chat. So from Jonas Tiemesland, on slide 18, how was the same factor introduced?
Okay, I guess I erased the slides he was mentioning.
Oh, sorry.
Sorry, can you tell me what it was? I don't remember now.
I think he can ask you the question directly. I mean. Jonas, are you here? Ah, he has no access to the microphone. So he put a formula. So it's phi double dot.
Okay, something like, where does the sign come from?
Okay,
ah,
fine.
the sign. Okay, sorry, didn't understand. Sorry. Yes, of course, the sign comes from the derivative of the cosine. Remember, we have the derivative of the potential. So let me see if I can show it. Now I have also the chat open, which I don't want to have anymore. Let's see if I can close it. No, how do I close the chat here? Sorry, I have to stop sharing, I guess, and close the chat and then reopen again. Sorry. Yes, so if you remember how this is the equation, we have the derivative of the potential. And if you remember the potential which I showed you before, it had a cosine. So if you derive the cosine, of course, you get a sine. It's nothing else than that. Yeah, here is the cosine. So this is the potential we get for the axiom. And then when we take the derivative of the potential, from the cosine, we get a sine.
Okay, I have one short question. I mean, compare with the lambda CDM is 200 MeV. The mass of axion can be very small, maybe at the macro EV, something like that. But in this case, the axion still be cold because the production mechanism is totally different, and the axion can never achieve a thermal equilibrium, right?
Yes, exactly. So this is the other advantage of this mechanism. If you see here, what I am producing is practically a coherent oscillation of the condensate, where in practice in the equation I took exactly momentum equal to 0. So that's why I call them 0 modes. And actually, you could also look what happens if you have some small momentum. It doesn't change a lot the discussion, so that's why I put exactly k equal to 0. It does you also some additional things, which we will maybe discuss tomorrow. The fact if you have some k dependence, you would also have some, of course, inhomogeneity, and you could have these what are axion mini clusters formed. So that in some sense you would have some over densities and under density in the axion field, which could also collapse and give you a particular type of structure formation. So this in some sense is not discussed here, but this depends also, if you want, on the history of the universe, and if you still have these inhomogeneities or not. And we discuss that tomorrow. But generically, it's correct what you say. These axions, which I'm producing here, even if they are incredibly light, they have no momentum practically, or momentum much smaller than their mass. So they are non-relativistic from the start.
Okay.
So you produce them already non-relativistic. So you don't have to worry about them ever being thermal or ever being, if you want, moving too fast in the universe.
Okay.
Can I ask one question about essentially? We said that the field value at the initial oscillation is linked to the misalignment angle during inflation. This is neglecting an harmonic effect of the potential.
No, so the initial value is the initial value. So this one does not depend on the harmonic effects. In principle, of course, the anharmonic effects could show up here. So here you could have a correction, and you can compute it. Of course, if you do the evolution numerically, you can also take the anharmonicity into account. And that, of course, would change a little bit the number density of the dark matter, if you want, depending on how far you are in the potential, so how far away from the minimum. And indeed, I can show a picture tomorrow about that. This would change this formula a little bit, but it's not a strong change.
Okay, thanks.
Yeah, so you can write here a function which is in some sense a correction connected to this anharmonicity of the potential. So this would mean taking the whole sinus and not just the first term.
May I ask something?
Yes, of course.
Before, when discussing the production of hot actions, you mentioned that it's an example of a WIMP mechanism.
Yes.
So what do we mean in general when we say WIMP mechanism? Is this kind of process all involving one particle at the end? Or what do we mean in general with WIMPs?
Well, with WIMP, it's meant a particle which is not in thermal equilibrium, and it is produced with a mechanism which produces a single particle, if you want, at the time. Well, you could also have twice, but it's a particle which, in some sense, is their number density is based on this Boltzmann equation, where you see that you have a dependence on the linear density, and where usually you neglect the second term, so that at the beginning you assume there is no particle or very, very little particles around. so that you have really the dependence and the, if you want, the source of the particles, it's coming from the rest of the thermal bath.
Okay.
I mean, tomorrow, if I have time, I will discuss it a little bit more in detail, because it's also a mechanism which is very popular nowadays. And in some sense, it's very similar what happens with the axion. The only problem or the only difference you can have is if you have really renormalizable or non-renormalizable couplings. So for the axion, of course, you have this 1/Fa, which gives you a non-renormalizable coupling. And historically, many of these FIMPs were of this type. On the other hand, if you want, the classical FIMP today is probably, well, I mean, I think there are different types, but it's more connected also to renormalizable couplings. Because the dependence in the temperature here for the cross-section, etc., it's of course different if you take particles which are interacting with a renormalizable or non-renormalizable coupling.
I see. Okay.
So if I have time tomorrow, I can discuss it, but I didn't really concentrate on those type of models because I was asked to talk mainly on WIMPs and axions.
So when people talk about fuzzy dark matter, they are really talking about this misalignment mechanism, not this FIMP mechanism.
No, they are talking about the misalignment.
Okay,
yes.
okay, just to understand the notation. Okay.
Yes,
Thank you.
and these thermal axion, it's actually something which was discussed in the very early days, but nowadays, as I said, it's also because you see that if you want really to have this fuzzy dark matter, the mass has to be 10 to the minus 20 electron volt. So you cannot generate the density you need from the thermal mechanism.
Yeah, I see.
Okay, so you see here. So if you have the fuzzy dark matter fuzzy dark matter is something with mass of the order of 10 to the minus 20 electron volt.
Yeah.
So from this mechanism, you would have zero density practically.
Okay. I
But
see.
from the misalignment, in principle, not. Of course, even there, you have to be a bit careful. Here, I wrote everything as a function of Fa. So if you want to have a very light dark matter and still have this misalignment mechanism working, probably you have to go beyond, of course, the Qcd axion. So in that sense, to have a very light dark matter, you have to take, instead of lambda Qcd, something much smaller.
Okay.
But we will discuss that tomorrow as well. Tomorrow, I will try to give you a bit of overview what happens if you extend it to ALPS instead of Qcd.
I have a question. So with this misalignment mechanism, as the axion oscillates kind of in its potential well, I don't know, I can imagine that you have inhomogeneities on your axion field that can get parametrically resonant or amplified, essentially, just like preheating, essentially. And that would
not really, because the coupling here is very small and the mass is not changing so fast.
Okay, yeah, of course, I see.
So you would need a coupling, another additional coupling of the axion to something else. Otherwise, you would not have something like preheating.
Okay, so your condensate is kind of protected in that way.
Yeah. Of course, I mean, as I said, you could have on inhomogeneity, and tomorrow perhaps we'll discuss that. This can give you overdensity or underdensity of axions, and this can bring to this formation of axion mini clusters, as they are called. So that is one prediction if you have sufficient inhomogeneities in the initial axion field.